Hello everyone, my name is Vasilis from University of Sussex, and I'm going to be speaking to you today about model checking software-defined networks with flow entries that time out. This work builds on earlier research we published in CAF 2020 that has used patch holder reduction in a contextual fashion to improve verification scalability for software-defined networks. The contribution of this paper is in proposing an extension which captures dynamics in software-defined networks related to time that elapses for flow entries that are installed in flow tables of the switches. And second, in proposing optimizations which allow model checking to be effective for systems with flow entries that time out and applicable to bigger settings. But first, let's have a look at the model we started with. Here we see a high-level view of the model in a simple two switches and two host topology. The model is based on an interleaving semantics where concurrency of functions is reduced to the non-deterministic choice of the order the parallel transitions are executed. The left half of the figure shows the open flow interactions in blue, and the right half shows the modeled actions, the red arrows, and the shared buffers. A red arrow depicts an action which, when fired, dequeues an item from the queue the arrow begins at and adds an item in the queue the arrow head points to, or multiple items if the arrow is double-headed. Deleting an item from the target queue is denoted by a reverse arrowhead. And the forked arrow denotes possibly multiple targeted queues. Now, having chosen as modeling mechanism for concurrency a communication which is based on shared state through interleavings, means that concurrent threads interact through reading mutating shared data queues. To give an insight to how packets, rules, and messages flow in the network, let's see a simple example. Suppose a packet is sent from a host to a switch. If there is no matching rule in the flow table of the switch, then the switch will ask the controller how this packet should be handled by adding the packet to the request queue of the controller. Next, the controller sends back instructions on how this packet should be treated, which is the packet out message. And a set of rules is sent as well in order to match further packets of same shape. Next, the packet is forwarded accordingly, the forward action here, and rules are installed or uninstalled represented by the add or delete actions. Also, barrier reply messages may be sent to the controller to update the controller state about the rules installed or removed. And the packet processing continues until it reaches the final destination. But why one may need timeouts in software-defined networks? The easy and perhaps most convenient answer is to model TCP sockets that can time out. That is, timeouts in which a socket expects to receive an acknowledgement for sent data before it decides that the connection has failed. To illustrate this, let's consider a load balancer which selects which server out of a cluster of servers should serve the TCP connection initiated by a client. This load balancer is stateful. That is, it keeps track of the active sessions between clients and servers in a cluster. When a connection is initiated by a client, for example a web browser, sending an HTTP request message to the web server, the controller will install the access rule 1, which opens a client-to-server connection. The server will start a return connection on a logical TCP port and which is allocated for short-term use. The controller then should automatically open the temporal port for this return connection by installing rule 2 with random timeout, and only then the server can access the client. Each of the two logical connections, or flows if you want, the green arrows 3 and 6, is represented by a mapping between TCP/IP socket pairs. A socket is an endpoint consisting of an IP address and a TCP or UDP port. Now, the pair of these flows, which are matched by rules 1 and 2, constitute a session. Next, when the amount of time specified by the timer elapses, for example, the keep alive timer for determining if the connection is still valid and terminate it if needed. So if time elapses, both rules are removed and a flow removed message is sent to the controller to refresh its state. This situation is a so-called soft state of the system, as the controller state has not yet been refreshed. The soft state goes away when the flow removed message handler is executed and the controller state is updated. Following the same procedure, the controller program assigns new sessions to servers according to a predefined schedule, either round robin or list connection or any other scheduling. In order to model such dynamics like the user inactivity we just saw, rules are enhanced with logical discrete timeouts, which is a timeout bit which, when true, the installed rule can be removed at any time. This allows to achieve a temporal ordering of rule removals. In a less trivial setting, to pose a specific temporal ordering of rule deletion actions, we allow timeout field to be bound by integers as well. Note that there is no time passing in our model. There are no clocks. Timeouts here are used to enforce certain orderings of flow removals. Of course, if timeout is set to 0, the flow entry does not experience a hard timeout. Each transition in our model is decorated with an action, and each action alpha is parameterized by a vector of references from the components of the system, which are switches, hosts, packets, rules, barriers, ports, and controller states, which all are passed by value. The argument's values are bound when the transition labeled with the respective action is taken. Now, our transitions are protected by guards, Boolean guards, which are enabling conditions, that is, predicates specified over the state at which the action is taken. Suppose rule R, which is a timed one, is installed in the flow table of the switch in state S. Then, the flow removed action can be executed, moving rule R from the flow table to the flow removed queue in the controller. Next, the sync action is enabled, which models the call to the flow removed message handler. As a result of the handler execution, the controller state CS may change, and in addition, a number of packets and rules interleaved with barriers may be sent to the switch. And this is the final model which supports timeouts. Here, the new components, the OpenFlow flow removed message and the respective encoded actions are highlighted. To check our model in an efficient way, we follow the approach of pruning the state space in terms of redundant explorations. And for this, we employ the contextual partial reduction technique that we proposed in our CAV paper, according to which a step might be independent between any other and invisible to the property only in the particular context explored. And we apply this technique to the new actions in our extended model. Context for us is a triple network topology, lambda, the controller program CP, and the property phi at stake. The ultimate aim, of course, is to find more safe actions which do not need to be interleaved with other ones. To illustrate with an example how an action might be safe only in particular context, consider the network in this figure and the property in two contexts. In context 1, the property is an assertion over the controller program state, given that the controller program keeps track of the flow removed messages and updates its state accordingly. As such, the property may be violated upon the execution of the action fsync when the flow removed handler is executed. This means that the action is visible to the property in context 1. This, however, does not happen with the property in context 2, which only asserts facts that happen in the data plane, that is, that never a packet with a specific IP reaches the switch. We evaluated the proposed extensions in terms of verification performance and scalability. For this, we used a realistic controller program that enables a network switch to act both as a load balancer and a stateful firewall. The load balancer employs a least connection scheduling by assigning sessions to the server with the least number of active sessions. In addition, the flow removed message handler in the controller rebalances the active sessions when a session expires and the load is about to get out of balance. This is done by moving one session from the most loaded to the least loaded server. At the same time, the load balancer only allows specific clients to access the cluster. The red one, for example, in the figure is a blacklisted one. The property that is checked here is that traffic from blacklisted clients is blocked and the traffic, that is the number of sessions, is uniformly distributed to all available servers, which is formally expressed by this formula here. In English, a packet sent from a dodgy address should never reach the servers, and the difference between the number of assigned sessions at each server should never be greater than 1. We checked this property, scaling up the topology in terms of clients ranging from 3 to 5 and servers from 2 to 5. The state space exploration is illustrated in this figure. Here, the white bars represent the optimized model and the narrow one inside the unoptimized model. Uncolored bars represent non-termination, which means verification didn't terminate within 24 hours. The results show that the verification scales well with the number of servers but not with the number of clients. And this was expected as more clients means more packets and by extension more sessions in the network. And the state space is in the worst case exponential in the number of packets and sessions. The results also show that for network setups with 3 clients, the partial order reduction optimization reduces the state space and thus the verification time by about half. Of course, for more clients, the reduction is far more significant. And that's all. For more details, I encourage you to check out our paper, the controller program pseudocodes, and the proofs. Thanks for your attention.